Oh yeah, the recording. I'm shirking my duties. Okay, thanks. So my plan is to talk a little bit about some work in progress I'm doing with Jean-Yves, also Mauricio Hibbert, who's a postdoc in Illinois, UIUC. The article should appear pretty soon, along with some code that does the stuff that I described. So basically, I want to tell you how you should be doing systematic studies of nuclear structure in the context of heavy ion collision. So the main problem I want to solve is the following. The fact that when you do these systematic studies, what you want to do is, you want to continuously change these properties of the nucleus and see what changes in the observables. But the problem is typically when you change these nuclear properties, the change in the observables is rather small, as we find when we do all these isobar studies. And so, at least naively, this requires many, many events, and these are very large statistical demands. I mean, I think the people that have done these things can probably agree that this is kind of one of the most significant bottlenecks for doing these kind of things that we've been doing. I mean, as we discussed in the last talk, like, one way of getting around this is you just use this initial state estimators for everything. You just run everything in Trento and then estimate what the final observables are. But as we discussed, it's, that adds some uncertainty that it's potentially hard to quantify. And just in general, if we could reduce this requirement, I think that would open up a lot of opportunities for study.
But my comment is that we can use this opportunity to improve our initial state estimators, because this sometimes if you're a single system, it's hard to know why it's not describing a final answer. But if we can even find a better estimator from initial state, that actually is really, really helpful.
Absolutely.
Yeah.
But so my claim is that I think we can reduce these statistical demands. That's, in fact, there are better ways to do it than the way we've done. And the way I would describe it is, think of experimentally when we did the isobar collisions, ruthenium and zirconium. By taking ratios of the two systems, a lot of the systematic experimental uncertainty cancels because it's correlated between the two systems. So if we can correlate the statistical uncertainty between two reference systems, we can similarly have a lot of the statistical uncertainty canceled. So that's the basic idea. And I think it'll be pretty short, so I expect, so just stop me and get lots of questions. There will be lots of discussion, but the slides will be short. So please stop me and discuss, if there's anything uncertain. So here's kind of the basic idea. So what you do now is kind of the following. So you pick a nucleus, you pick some set of parameters, which is usually like a Wood-Saxon parameter, plus maybe an exclusion distance that sort of mimics short-range repulsion, short-range correlations in your nucleus. And then you sample that distribution to generate some set of discrete nuclei that each contain some discrete set of nucleons that represent the statistics that you wanted. Then you collide them, compute observables. And then if you want to see what happens when you change nuclear parameters, you sort of start from scratch. You choose a new set of parameters, then you generate an entirely new set of nuclear configurations from scratch, do more collisions. And then if you want to know what is the dependence on these parameters, you maybe take ratios of observables, but the statistical uncertainty in the numerator and denominator are completely independent. And so if you want to detect some small change or some small change in parameter, you're going to need lots and lots of statistics. So what's, I think, a better way of doing this is you do the first step the same. You generate some discrete nuclear configurations, but then you just do it once. And that corresponds to some set of statistics, some nucleus. And if you want to study some other nucleus, or what happens if you modify a parameter, you can actually generate a new set of nuclear configurations that satisfy the statistics that you want. But instead of starting from scratch and doing it independently, you can actually obtain it by taking the set that you already have and modifying them just by changing the positions of the nucleons a little bit.
You're going to tell us how these shifts are unique.
Yes, well, unique. No, they're not unique. They're not unique. That's definitely the case. But that doesn't mean it doesn't work. I mean, there could be different solutions. But I will show you that it works. That you have the set of nuclei that you have that satisfy the statistics that you want, both the one body and two body distribution. Well, all body distribution, you can argue. And that the statistical uncertainty is reduced.
So will it capture all types of fluctuation? For example, your position fluctuation that you can capture by this shift to the nucleon position. What about, like, let's say you have color chart density fluctuation? Will it capture that?
Good question. I mean, not in this method. So what I'm going to talk about through most of the talk is just the fluctuations that come from nucleon positions, which typically is the most important for us, for most observables that we care about. But I will argue that, so it depends on what kind of fluctuations in your model, but other fluctuations, you should also try to synchronize as much as you can in ways that make sense. So we can discuss, I haven't thought too much about color chart fluctuations in IP plasma, but we can discuss how to do that. Anything else I didn't say? Yeah.
Typically,
Oh, yeah.
We'd like to translate your nucleon by keeping the quark in the same position, right? That's definitely.
Yeah, I mean, so to get to zeroth order, you still, the most important is still the positions of the nucleons. But if you have then extra fluctuations on top, maybe there's nice ways of synchronizing those as well, which I haven't thought about too much in the plasma case.
There are some trivial or pure. I mean, if there's some fluctuation which you think is the same between the alpha bar, then you would like them to actually cancel by design. So otherwise, you introduce additional arbitrary state.
Yeah, you really want to synchronize
Yeah.
the fluctuations as much as you can,
Yeah.
and sort of reuse the random numbers that you use that you
Only
generate.
capture the source of fluctuation or correlation, which is dependent on nuclear structure. Right? That's the goal.
I guess one thing I wanted to just say right away is that this is not only for the one body distribution. So the radius, the diffusivity, and the multiple coefficients, but also we can use the same method to study sort of arbitrary short range correlation function. So
Pauli exclusion for overlapping nucleons.
yeah, so you can just implement, you can just say, I want it to obey this correlation function, this two body distribution, and study it. So even without all of the advantages about statistics, I think there are a lot of advantages to this compared to just doing like an exclusion radius and things, which I can discuss as we go. All right, so this is an outline of the talk, but also sort of an outline of how it works chronologically. So you start by, well, at least the way that we implemented it, we start by implementing a spherical nucleus of uncorrelated nucleons with some arbitrary Wood-Saxon radius and skin thickness. And then with that nucleus, we modified those distributions to obtain whatever other one body distribution you want with deformations, beta 2, and any multipole, any radius, any diffusivity parameter.
So when you say with uncorrelated nucleons, you allow the nucleons to sit on top of each other.
Yes, in the first step. Yep, they're totally uncorrelated. But in step 3, we can add whatever correlations you want, including complete exclusion. Yeah, so step 2, then we modify the one body distribution. They're still uncorrelated at that step. If you want correlation functions, then we add that in step 3. I'm not really sure how important the ordering of 2 and 3 are, but this is how we do it. At least in my mind, it's easier to understand what I'm doing when I do it in this order. Then for the talk, the last part of the talk, I think, which is also important, we want to try to sort of get some benchmarks and get some idea of like, how useful is this? What kind of speed ups does it give us? So let's do that. So this is actually kind of an aside because it's actually totally not essential to anything that comes after. But at least for our implementation, we used not exactly a Wood-Saxon to sample. We used something different, which is a good approximation to Wood-Saxon in the parameter range that we care about. And it's just kind of nice for a lot of reasons. So it's not essential to this talk, but I wanted to present it just to see if there's any interesting feedback or to see what you think. So the idea is the following. So the position of a nucleon in the nucleus is given as the sum of two random vectors. One of them is a random a vector given by a random, let's say, a 3D step function parameterized by some radius of the step function. And then the second is a three-dimensional Gaussian parameterized by a Gaussian width. So the idea is kind of the same as what I think the Wood-Saxon is supposed to be. It's kind of this uniform density in the middle and then plus some fall off at the edge. So if you do a sampling like that, the distribution you get at the end is a convolution of those two distributions, which if you work it all out, looks kind of like this, which is a little bit longer and messier than a Wood-Saxon, but it's actually a lot nicer analytically. If you want to do any sort of manipulations, it's it's smooth at the origin. So that's about it. So we use this as an approximation to a Wood-Saxon basically in our simulations. It's also a two parameter distribution. And we choose the two parameters by minimizing the relative entropy between the Wood-Saxon you want and this actual distribution. Which you can see does a pretty reasonable job of mimicking a Wood-Saxon.
What do you call the relative entropy?
It's a Kullback-Leibler divergence between the Wood-Saxon and the step plus Gauss. So it's a way of quantifying how different two probability distributions are. It's not really a metric, so you can't think of it as distance, but it's like a distance. So it's non-negative. It's zero only if they're identical distributions, and it's larger than zero if they're different. And how far away from zero tells you sort of how different they are.
I think it's proportional. It's the average of the square of the relative difference between the two.
Is it? Okay.
Yes. With a factor 1/2.
I know it is coming kind of, it comes kind of from
So it's
information
really-
theory. There's a reason it's called entropy. But
No, but this is where it comes from. But for us, it's really you just for distribution that differ very little. You do a leading order expansion and it's a relative
There
difference.
is no logarithm involved.
Yes,
Yes.
you expand
You expand the log.
log plus epsilon or 1 plus epsilon gives you minus epsilon.
oh, so if they're close, then you can.
If they are close, it's really
I see.
the average value of the square of the difference, the relative difference.
So I don't know. It seems quite a reasonable thing to use. It's pretty standard. And but if you have some other thing, if you think this is not really the one that looks the best to you, like maybe you'd rather have that better and at the expense of something else, we could use a different definition. But I don't think it really matters. So yeah, the rule of thumb, you get this, but in practice, we just dynamically on the fly we get the parameters by minimizing scale divergence. If there's anything else to say about that. And then yeah, so if the skin thickness gets larger and larger, then this step plus Gaussian is less able to get the same thing that a Wood-Saxon gets. But I think for the parameters that we care about, I think it's good enough. And it's not really like there's anything magical about the Wood-Saxon anyway. I don't think. I don't know if is there a reason to believe that a Wood-Saxon would fit like a density that comes from your calculation better than like the red curve.
I would say maybe the way to test is like take a DFT distribution and see how well it can minimize the difference.
The main problem with the Gaussian is that it falls off too fast at large distances. So that's the main problem you have here. Tails are.
Okay, so it'd be better to use something other than a Gaussian maybe. Although that would make things harder probably.
But in the DFT with the tail, they fall exponentially instead of
Should be.
radically,
Should be more.
more exponential.
Okay, and it's just nice for a few reasons. So One nice thing is like you trivially can change RNA without doing the method that we're going to describe, which will involve just doing numerical integral. It's not a big deal, but it's nice. You don't need any acceptance rejection, sampling. You just sample uniform numbers and Gaussians. Also, the reason we actually started using it a long time ago is it has a completely trivial relation between the point nucleon density and the charge density. If you assume the charge is a Gaussian, then the convolution between two Gaussians just changes the width a little bit. And it's completely trivial. So that's kind of nice also. And it's just nicely analytic in general. But maybe we should move on to more important things. So now we sample a bunch of nucleons according to that distribution. A bunch of nuclei, which each contain some discrete nucleons. And now we want to modify it by shifting positions a little bit to get the one body distribution that you want. Still uncorrelated nucleons. So despite using that other distribution, we still parameterize everything with the Wood-Saxon. This is sort of the standard way that we do things currently. So this is the Wood-Saxon that we typically use with the radius, skin thickness, and these multipole coefficients, deformation coefficients, which you usually understand as taking a spherical Wood-Saxon and then modify the radius. So it's sort of a surface deformation. But I write this all together just so I can write this expression and say that I can write the same thing just by also transforming the coordinate r. So if I write the spherical distribution like this, then I get the deformed distribution. What I want to do is I want to define a continuous transformation. So I want to take a continuous parameter t that takes you from a spherical distribution, which is what we started with, to the distribution that you want, which will be t equals 1 in this formula here. And now the idea is going to be taking nucleons and transporting them, moving them from here to there, or in other words, we're transporting probability. So when you do this, when you change t, when you do this transformation, the density has to obey a continuity equation. And so that's basically the entire key. So we just want to solve this continuity equation to figure out how much the position of the nucleon should change given some change in t. Yeah, and if we just solve that, move the nucleons, then we should be able to end up with exactly the one body distribution that you want. So we start with uncorrelated nucleons satisfying spherical distribution with some RNA, and we end up, well, sorry, yeah, and then we end up with, in this case, we end up with a distribution with the same RNA, but arbitrary deformation. At least in our case, we changed RNA by doing the sampling of the stepless Gauss.
What's V in this?
Yeah, so V is d dx dt. So the change, given some change, infinitesimal change in t, that's how much the nucleon position should change. And so the simplest thing to do, which actually works pretty well, is just to set dt to 1. Just do it all in one, just jump all the way there in one step. And so dx is v times 1 times dt.
This ensure the density is constant in the center.
Oh. No, the density is not constant. The total number of nucleons is constant.
Yeah, the density is what you want it to be.
Yes, but since you transform from this density to another one, they have both the same density in the center, right? The default one.
Approximately.
You're transforming one to the other.
Because the in the center is flat.
Yeah, you do.
Yeah, it's still flat both before and after. It's very flat in the center.
Okay.
It's just, but it's just whatever you specify it to be.
It's a continuation. Okay.
So you have a proportionality in the second line on the left side.
Yes.
Where did that normalization go in the?
Good question. So the normalization changes a little bit. They're not, it's not the same on the first line and the second line. But it's basically just a negligible effect, I would say. Plus the fact that it's the normalization just is there, is determined by the fact that your probability sums to 1. And since we're doing everything by just by transferring particles, probability is automatically conserved. So it's not, it doesn't mathematically cancel, but it essentially cancels in the formulas that I'll show you.
So what you're saying is when you're solving the continuity equation at the bottom, you don't get rho of r minus, but you get this multiplied with an overall constant.
Yeah, that's a tiny bit different. I mean, it's really negligible, but you're right, strictly speaking. I tried to just, gloss over it.
Yeah, try to cheat us, I know.
I might cheat you a couple times today.
Try to catch you.
But I would say, some of this is just to get you to understand like how it works. But at the end of the day, when you implement it in Monte Carlo, you check the statistics of the nuclei that come out. I mean, and if it works, it works. Like it doesn't really even matter where it came from necessarily. Yeah. So, but just a little bit about how we solve it. So this is a single, linear differential equation for a vector field here, V. So it is. So as I said before, it's not unique. This is an underdetermined system. There are many solutions that you could find to this differential equation.
So that's what I don't understand. Isn't the V given by your initial distribution?
No.
Okay, so what do you have to do in order to solve this? Do you have to give an initial profile for V?
No, you just have to set boundary conditions.
Okay, what are the boundaries?
Well, so what we do, so all we need to do is find a solution. But it's also important to find a nice solution. You don't want things that are blowing up and stuff. But otherwise, if you find a solution that works, then it will do the job.
So you're trying to define a diffeomorphism that produces the change in the density.
Yes, and it's not unique.
Yeah.
You don't necessarily expect it to be unique.
It should look like you're finding vibration or solution.
So
vibration.
anyway, what we do is we look for a solution like this, basically irrotational sort of flow.
Yeah.
Just because it seemed nice. We can't. I mean, again, all we need to do is find a solution. We can't prove that's the right thing to do. It's just a nice thing to do. Then we take this scalar field and we decompose it into a spherical harmonic basis. And if you solve this whole thing starting from the spherical case.
Does that include an ln equals 0, term?
Yes.
Okay, so it's different from the sum on top, which has only L non-equal 0. The first line on the
yes.
top has only L non-equal 0. The phi has L equals 0.
Yes. I think that's right. I have to think about it. But anyway, if you just plug this in for this case where you start from the spherical distribution, all the harmonics decouple. So you just get this single one-dimensional differential equation. Basically you can do it analytically at very small and very large R and figure out what the boundary conditions should be so that it never blows up and it's always just kind of nicely behaved. And so this is the right thing to do. I think we should probably move on, unless there's like, oh yeah, so just like how does it look? So these are just this is a slice at y equals 0 in the xz plane for a couple of examples where the only non-zero beta is beta 2. And these arrows tell you basically if you have a nucleon that's at the base of this arrow, you move it to where the head of the arrow is. And that will take you from a spherical distribution to a distribution that has beta 2 equals 0.2, which you can kind of see from you go from the dashed line to the solid line, or for beta 3, and so on. One interesting thing to point out, which will be kind of important later, is that the nucleons in the center don't really move at all. It's kind of all done by moving the outside. And this will kind of be important for limiting how the improvement, the statistical improvement, because these ones on the outside are kind of more important for getting eccentricities and things. But don't worry, you'll still get a good improvement. Just useful to keep in mind. And yeah, as I said, as long, however you got there, as long as you have the right nuclei at the end. So we we started with uncorrelated and we ended up with uncorrelated because the entire procedure was completely independent of the position of any of the other nucleons. It just depends on the original position. The two body distribution is trivial. One body distribution is what you want it to be. So these are the examples from the the famous ruthenium and zirconium parameters that we've seen this whole time.
So in the right plot, you denote relative density. What is relative?
I just wanted a 1 here. I don't know. There are better ways of comparing it. We use this relative entropy to quantify exactly how different all the distributions are. But this is just sort of an
Okay, this
illustration.
doesn't, the right side, does that compare with Saxon with Monte Carlo? Or it only tells you how.
This is the
how
wood
well the
section,
sampling- Oh,
I think.
okay.
Yes, this is not the step plus Gauss. This is the actual wood Saxon. So yeah, this is a plane through the middle. There's densities, and then this red line tells you where this red line is. It's just like a line right through right at x equals 0 as a function of z, and so on.
Why do you get these large fluctuations at small x and z? On the Carlo?
They should be, the size of the fluctuations should be the same everywhere. It's just that it's
You just
falling
don't
so
see them
fast that
on
you
the
can't see
screen.
them. Because I just broke it up into cubes of 0.1 Fermi on a side and just counted up particles in each cube. We can definitely do better if you want more precise measurement of how good it is, but this seemed
So
good
this
enough.
just one slice, right? One narrow slice.
This
and
one,
compare-
yeah, so the red
compare
line
between-
is like right where this red line is. That blue line is right where that blue line is.
Compare between what? There's
Exact solution.
there's exact solution. and
There's
Monte Carlo.
the wood section that you wanted it to be, and then the sort of numerically averaged from the Monte Carlo, what you actually get.
This is for how many samplings? How many events?
Good question.
You said 400K.
Yeah, 100,000 nuclei. Excellent. Thanks, James.
Thank you. What's the wrong color?
Good answer.
Sorry, I'm missing, why is it more bumpy in the middle and not so smooth on the sides?
I don't believe it is. I think you just don't see it because it's falling so fast. It should be kind of the same everywhere. But I think we better get to the correlations, because those are also more interesting. Let's see, we got 15 minutes, that's okay. Okay, so nucleons actually can be correlated, especially because of short range interactions or just like Pauli exclusion and things like that. So we define this correlation function like this, where this is the two nucleon probability distribution. This is the one body distribution that we were discussing before. And if the two particle distribution just factorizes, then the correlation function is 0. So they're uncorrelated, which is what we had, but they can be correlated. And so what we want to do is induce a correlation, some arbitrary short range correlation function, by starting with an uncorrelated set and then shifting particles again to end up with a correlation function that you want, or a set of particles that obey that two body distribution. So it's kind of going to work like this. We're going to go pairwise and see what's the distance between the pair, and then ask how much should we change that distance between the pair in order to affect this correlation function. And then when we actually implement that, how do we change the pair? We just do it in a symmetric way where we change one by half that amount, and we change the position of the other by half that amount. And what we do is we calculate all of these shifts. We calculate what all the shifts should be from all the pairs before we do any of the shifts. So we calculate what are all the shifts that this nucleon should have based on its pairings with all of the other nucleons. And then we just kind of do a vector sum of all of those shifts.
Are you assuming that the correlation function depends only on the distance R12?
We will.
Okay.
I mean, I kind of wanted to, yeah, I kind of went back and forth. I wanted to make the equations general because I think the method does work just fine if it's not. But of course, what we do and what I was kind of more interested in is just a central correlation function. So what we implemented was just a central correlation.
So at
function.
the bottom, that the direction is proportional to the unit vector Rij. means
Yes.
that you are assuming that it's just a distance. Correlation depends on the distance.
Well, I think we would still do it this way, even if the correlation depended on the angle. I think we would still.
Why would the shift then be along the line of connection?
I mean, I don't know, I haven't thought about it that much. I still would think that all we would want to do is change the distance between particles.
Okay.
We wouldn't want to change the angle that they have. We would say, based on the angle that they have, how much, so the distance that we want to move them would depend on the angle, but I don't think we would be changing the angle.
Okay. Okay.
But I don't know, I haven't thought about it too much, so maybe I should just say, let's just do spherically symmetric correlation functions. That's all we really did anyway. So here's how we figure out how much we should change the distance between the particles. So we start out with a pair of particles that have some distance r here, and then r tilde is the new distance that we want them to be. Okay, so again, we're transporting particles, so the number of pairs should be conserved. So what we want to do is build up a continuous function. R tilde is a function of r, starting from 0 out, if we get this monotonic function. Yeah, we do it so that we ensure that the number of pairs of particles in some at maximum distance r in the uncorrelated case is the same number of pairs as you get in the distance r tilde after correlation. Okay, and so all you need to do is invert this relation, solve for r tilde. So these integrals are trivial, just get the r cubed. And then this, of course, depends on what your correlation function that you want. So if you want to just do it numerically, you can put anything you want in there. We actually, for even simpler, we just have this 2-parameter step function, correlation function that we put in so far, so that you can vary both the length of the correlation, but also the strength. So you can go all the way to full exclusion, which is essentially equivalent to the exclusion radius, but you can also vary it.
So basically, you are creating a hole, or maybe not an infinite deep hole, but a hole around each nucleon, in which no other nucleon can sit.
Yes, if you set this to -1, you get that effect.
And
Yes.
that would be a naively expected effect from some kind of Pauli exclusion principle.
Mhm.
And it makes a lot more sense to implement that after you have done the moving of your particles than before.
In my head,
Because if you
yeah.
did it spherical before, it would not end up spherical afterwards.
Yeah.
which
I
would-
think in the end, the result you get will probably be pretty much the same.
Yeah,
but-
but it would
We are doing
be a really unintuitive
Yeah.
No, but,
form of the exclusion.
Definitely unintuitive. Yes.
I think we are doing a perturbative expansion to leading order, so it's linear. So we're
Yes.
doing a linear expansion in the deformation and a linear expansion also in the correlation. So this is linear. I think it's
Yeah.
good.
I think that's the key. Everything we're doing are small changes.
What do
So
you mean by
really,
that?
I don't think any of this
I think
matters.
I mean, this map, this creates spherical holes in the modified, in the deformed nucleus.
Mhm.
Whereas if you started doing it the other way around, it would create octopole deformed or elliptically deformed holes in the deformed nucleus, which is
But it's a
Strictly
small,
speaking,
we are assuming that the correlation is small, so that this only works if the correlation is the correlation volume is much smaller than the volume of one nucleon. And it also works only if the deformation is small. So I think it really doesn't make any difference to me mathematically. It's just a
But we do it the way you like it anyway, so everything's good.
Your correlator depends only on the distance between the nucleons, right?
Yes, right now.
You have also.
I do. I mean, I haven't spent a lot of time thinking about it, but I'm pretty sure you can do the same thing if you want it to depend on angle or spin or whatever. I don't
Yes.
think much changes.
There are some also tensor correlations in the.
That too. I think all of that could be done in this pretty trivially.
Yeah, but from the point of view of the heavy ion collision, you don't actually know, you don't care about the spin or the proton or the neutron.
Exactly. No.
So this
That's the point.
So somehow just I guess we could probably just boil that down to an effective radial correlation function probably, because we don't really have any sensitivity to any of that stuff. But I think you can use this method for much more complicated things if that's what interests you. This is what we have so far. So just one little caveat. So we don't actually do quite this. This plot is actually correct by the eye, but we don't do quite this because you can't actually have this correlation function. So the number of pairs is the same in every event, or so at the level of the way that we wrote this, these are probability distributions that are normalized to 1. So if you integrate the left side, you integrate this guy, you get 1. You integrate the left side, the first term gets 1, which means that if you integrate over the correlation function, you have to get 0. So it has to change sign. There's sort of a sum rule there. So even if I tried to implement the thing that I showed you on the last slide, that wouldn't really be what we get, because you have to have something that satisfies this property. So at least the way that we take care of this is we just take whatever short range correlation that we wanted it to be, and we just add a tiny little constant to it. If it doesn't satisfy this, then we add a little constant that takes care of it. And it's actually kind of nice, actually, seeing this in action, because that actually goes a long way towards keeping the one-body distribution fixed. If you just do the naive thing and you say, I take all pairs and I'm always just moving them apart from each other, then you're expanding the edge of your nucleus, and you can see this. But if you make sure that this is satisfied, that actually fixes that.
That means that your correlation function is non-zero all the way to infinity.
Yes,
That's
by a tiny bit.
unphysical.
Tiny bit.
Yeah, we could do something that you consider more physical, but
the nucleus is finite. I think if the nucleus was infinite, this constant would be 0.
yes, that's right. If the nucleus was infinite, then the constant would be 0. That's true. So it kind of cuts everything off. And you could do something different. We could certainly discuss that. But I think this.
When you look at the work by Strickman and collaborators a few years ago about including two-body correlations, the correlation functions, they looked like that and then they fell off.
Yep.
So could you do something like that here too?
Absolutely. Yep.
So I mean, you do want to create a neutron skin, right?
So that was in the previous section, the neutron skin. I mean, we don't really know anything about the difference between protons and neutrons. The only way the neutron skin really comes in is just how the density falls off at the edge of the nucleus. So this sort of diffusivity parameter, and we can make that or whatever you want in the first section of the talk. Oh yeah, so a little bit about the correlation function. So I guess just verifying that it kind of works. Here's the basically the correlation, the two-body distribution, and the one-body distribution. Just showing that you can have an arbitrary both length and strength of the step function and get basically what you want. These, I don't know, interesting choice, because these basically have the same effect. What you really care about is the cube of the correlation length times whatever the strength is. So if you multiply the length by 2 and divide the strength by 8, then you actually get basically everything's the same. You can't really even tell the difference. Results and the one-body distribution. It's pretty good. It gets worse if you make this that volume.
The difference in which results?
With the eccentricity ratios that I'll show you. So yeah, I'll show you that'll be an important part also.
Can you calculate, I mean, you have the distribution, but you can also calculate the first and second moments of this distribution to see whether the size and the
Yep,
skin change.
you can quantify the change, yeah.
Quantify that, yeah. Because there are some differences.
Yeah.
It's hard to tell if
This is small compared to what people usually do.
Yeah, but if skin change by 5%, that's a big change. This look like it could be changing by that.
I can calculate it for you. But maybe we should jump ahead to, so yeah, you want to know like what good is this? Does it do any good? How useful is it? The bottom line is you can get very significant benefits, but it really depends on context. So it really varies, and so there's some discussion to be had about that, even though we don't really have time for it. Okay, so what we did just as a first step, just to sort of like get some intuition for how much effect this has, how much speed up you can get. We did the following. So we just implemented some simple participant Glauber model, calculate participant eccentricities in a Glauber model, just set it to zero impact parameter, mostly because it's simple, but also central collisions are probably the most interesting location for these things anyway. All right, then we calculate eccentricities, RMS eccentricities, and we take ratios between some baseline nuclear parameters and then some other nuclear set of parameters, which what I'll show you is a baseline, and then we just change one parameter by some amount in different amounts. Okay, and then you calculate those ratios. So like, yeah, just the example, here's the epsilon 2 ratio comparing a correlated system with these correlation parameters divided by the uncorrelated system. And then you want to compare that ratio.
So what's the parameter that you have changed here?
The correlation. So the denominator is totally uncorrelated nucleons. So there's no correlation. The correlation function is 0. And then the numerator is the correlation function is the step function with length 0.4 Fermi and it's full exclusion. Yeah. So this is basically like an exclusion radius of 0.4 Fermi. And then you want to compare the the method that I proposing to the usual method where everything is independent. Okay, so you can already see there's a difference.
Is that the band is the statistical error bar?
Yeah, so I estimate a statistical error bar with the jackknife resampling, just by removing events one by one. And then I just want to define this improvement factor. So answering this question, if I get some given statistical uncertainty with n events in the independent case, how many events do I need in the better case to get at least as small a statistical uncertainty? And that factor, that number here, I define as the improvement factor. What factor fewer events do I need? If that makes sense. Does the definition make sense? If so, then I'll jump straight to the actual.
But before you go there, I mean, if I look at the blue band and the pink band, the blue band is always at the lower edge of the pink band. So there is a systematic shift. Shouldn't you expect both of them to give in the limit of infinite statistics?
Absolutely, they will match each other in infinite statistics. This one eventually approaches blue, but as you can see, the error on the orange one is
why the orange
is still large even at 15,000 events.
Why is it lopsided?
The error?
I mean, why does the independent method approach the blue line not from symmetrically from both sides, but
it's because when I go from 10,000 events to 10,001 events, I didn't start from scratch and generate 10,001 new events. I'm just adding an event. So this point has 10,000 events, and the next point is the same events, but I added another one.
Memory from
yeah. But it still, I think, gives you an accurate estimate of what is the uncertainty at that point, just by doing the jackknife resampling of those events.
This is just one simulation with the 14,000 events, actually 15,000.
100,000, but yeah. Well, I mean,
you didn't go all the events.
Making this plot is actually kind of takes a lot of computation because you have to do 15,000 events and you have to remove one event, calculate all the observables again, and then do that 15,000 times. And if you want every single point, then you got to do that for 15,999. So yeah, I only did this plot up to here. But for the next plot, what I did was I took 100,000 collisions, and I calculated the error bar, the statistical uncertainty on that 100,000, and then scanned backwards to say how many events did I need for the better case. So like this top line, for example, I get some certain uncertainty 100,000 events in the independent event case. And I get a better uncertainty with 35 events using this method. So that's what these numbers mean. So yeah, I plot it. Yep.
What is, okay, you're going to explain the parameters.
Yeah, so this is so all of these correspond to full exclusion. So the strength of the correlation, or the parameter they call that anyways, -1. And I just changed the length. I changed it in a way so that the length cubed gets multiplied by 2 at every step. So you actually can kind of see that the effect scales exactly like C cubed. It jumps by a factor 2 every time. So this is the change. When I change the C cubed by this amount, this is the change in epsilon2. This is the improvement factor that I mentioned. And I showed this just because it's related to how much improvement you get. It's what is the average amount that each nucleon moved when I implemented that change in the parameter. You can see that the more you move nucleons around, the less improvement you get. Basically, you can get very significant improvements, but it does vary. And basically, if you have much bigger changes to your nucleus, you'll get less benefit by doing this. And I believe that the main thing that limits the improvement is when you move particles around, then participants become spectators or spectators become participants. So then you don't have a synchronized, you don't have an analogous nucleon in both collisions. They kind of disappear and appear a little bit. And so you lose the correlation and the statistical uncertainty. So the statistical benefit reduces a little bit.
So this is a computation between the correlation you introduced versus the random fluctuation in the original spherical system, right? You hope that this random fluctuation totally cancels, so you only identify this correlation effect.
Yes, that's right.
This tells you if you have a large correlation effect, this shadows the statistical.
Yeah, if you change things a lot, then
it makes sense.
yeah. Yeah, so actually, if you take the cross section and just pull it up to infinity so that everything's a participant, these numbers explode. You basically get perfect knowledge of the change. So I think the main thing that limits your benefit is the fact that you start changing participants to spectators and vice versa. But yeah, so you can get very, very big factors here, or if you do bigger changes, then you get less improvement. But I do want to emphasize that you always get an improvement. So there's basically no downside. I think it's the way that it should be done. And so I show these first because they're a little bit better. Then I wanted to discuss betas, although we're running out of time a little bit. So actually, I probably should have plotted beta squared because that's what matters. Yeah. But anyway. So yeah, so you'll notice these improvements are smaller, even for the same change in epsilon, and actually also for the same average shift, which it was a little misleading to plot this because it's not really necessarily the average that mattered. So to explain that, I wanted to go back to that plot way back, right here. So what happens when we do this, when we modify the shape of the nucleons? Well, actually, most of these nucleons in the center don't move at all, and then these on the outside get shifted. And so the average is a little misleading because most nucleons don't move at all, and then these get moved more than the average. And then also these are at the edges, and so they're more important for determining eccentricities. So that's the reason why the numbers seem to look worse for the beta cases.
That ratio, the improvement. Can you go to the last slide?
Yes.
This is the improvement factor for epsilon 2, right?
Yes. Yes.
And when you do the beta 3,
For epsilon 3.
oh, that's.
Oh yeah, sorry, I didn't explain that. So in
I see.
in these plots, this is the change in epsilon 2 and these epsilon 3.
Okay.
Although actually the numbers, at least these numbers, hardly matter. Like they're the same whether you look at epsilon 2 ratios or epsilon 3 ratios. But it just seemed more natural to do epsilon 3 for these and epsilon 2 for those.
So, very good.
So, yeah, I think that's the most important thing. So if you, basically the bottom line, if you make small changes to the nucleus, you can get very significant, like orders of magnitude speed up. But if you make very large changes to the nucleus, then it's much more modest.
So when you're saying that this really works or it's important once, as long as the change in the average change of the two between the two nuclei involves scales of less than 0.24.
It gets more important as the scales get smaller, yes.
Yes.
But it's always a benefit. So I don't want to be too pessimistic about it. I want to be clear that like it's always a benefit. You always have an improvement. But if you want to estimate like how many events do I need, then you might have, you have to think a little bit about what's your specific context.
But you don't want to do that going from lead to deuterons.
Right. Yeah, we didn't even discuss that. What happens if you want the number of nucleons to change? So you can still do things that make things better. But yeah, the more things you change, the less benefit you're going to get.
The idea was to study the sensitivity to nucleus structure for a given nucleus.
Yeah, so it's useful for isobars like collisions, but also just for a single nucleus. What you want to do is vary parameters continuously and see what changes. And so you need to do things like this for that. Yes.
In terms of absolute scale, so how long it is? It's improvement. How long does it take?
So it depends on the model, right? So what you see most of these 2 weeks are we just run Trento initial conditions and then we estimate the final thing from that. And Trento, like it's really fast. So people are doing tens of millions of events per point. And I don't know, someone can probably jump in and say how long that takes, but not very much. But if you start wanting to do something better, you do full hydro simulations. Then if you need to do tens of millions of events, that's like really significant. I don't know.
Yeah, but I mean, here you change the position. It doesn't affect the hydro.
Well, the
It
hydro
does.
get
It's to
changed.
change the initial condition.
Yeah, if you change the initial condition, you need to run the hydro to see what
Yeah, that
changes.
takes long. It's not the sampling of the nucleons.
No, but if you can do that with if you can do the simulation with a lot fewer hydros, that's the point that you want to make,
Yeah,
because the statistical uncertainty is
exactly. So if you do something like this, you could potentially do like a real Bayesian analysis with full simulations. Whereas if you didn't do this, I mean, I don't even know if it would be possible. Like it's really hard.
I mean, one of the limiting factors in the hydro simulations is that you have these quantum fluctuations in the initial state that are irreducible. They are not statistical. That you cannot get around from this. You will still have to do a few hundred events per other model parameter in order to sample the initial fluctuations in the initial distribution.
But the assumption is that quantum fluctuation are the same in the bar.
Well, yes. So you have a fluctuation in the zirconium, and you have a correlated fluctuation in the ruthenium. So you have to do that sampling only once, not for both systems.
Yes.
Right.
To get from one to the other system, you do the fast way.
So I mean, at each point in parameter space, you need whatever number of events you need to get some observable, but you need fewer points in parameter space.
So make this useful, you want to provide this code where we start with before the replace the Monte Carlo clover, basically, right?
Yeah.
That'd be really good.
So just a quick comment about the code. So we have a code. So all this will be ready pretty soon. And the code generates nuclei according to whatever parameters you want. And then it just gives you a HDF file that is exactly the same format that default Trento reads in, which is convenient. But I really want to make a warning that it's not plug and play yet, because Trento right now will just erase all the differences, because if you just plug it into Trento, even with a fixed seed, every event will have a different impact parameter that won't be synchronized between. It'll have different orientation angle. So we have to still go into the code and synchronize all the other fluctuations, which is in principle is not difficult, but it's just getting the code and rearranging things. Some of it has to be rearranged a little bit. So it'll be very useful for plugging into Trento, but not right yet. If you have other models like IP plasma, then you have to think about what fluctuations are in there and how do we synchronize them correctly.
Are there questions online? Probably need to go for lunch. Yeah, let's go, let's finish and come back at 2.
Okay.